Before getting started, first few words about who we are. Myself Sandeep and Karthik has joined along with me. We both are currently working as senior data engineers at Tiger Analytics. Tiger Analytics is an advanced analytics and AI consulting company. The current talk on Containerized Stream Engine is part of Tiger Data Foundation products, which is an in-house Tiger IP asset. So here is how we would like to spend next 25 minutes with you. The objective behind building this product, what are the design considerations and discussions that we took while building this product, how the infrastructure has been provisioned to make it reliable for any platform. We will also talk about detailed solution and CDC logic flow, and how we monitor and debug the analytic workloads, and some of the points to be noted and then best practices. So for any questions, you can feel free to post it on the chat windows. So how many of you are working with most recent data from business and taking real-time decisions as part of your analytics workloads? So not an easy thing to achieve it, right? So, but nowadays, business needs most recent data to make correct decisions rather than working with historical data. But every business depends on multiple sources of data to make the decision. And all these data are stored in different layers. So our objective is to build single source of truth for the enterprise level data. And all analytics workloads can act on the centralized data hub. So having the objective in place, we will see what are the design decisions that we took to build modern data pipelines. So these are some of the common ways to capture the data from business. Direct JDBC. In this method, we are directly connecting to production database via Scoop or any other JDBC utility. This leads to increased load pressure on source database, which will impact our production application. Also in this method, we cannot capture some of the DML operations like deletes, schema changes, as well as we only get the snapshot data. The second method is dual writes. In this method, we will write the data into production database and any pub, and also to a pub subsystem like Kafka. And this data has to be streamed into Data Lake to perform any analytics workloads. But due to dual writes, there are two copies of data needs to be written to two different systems. So there might be some performance or latency issues on production applications. The final method is change data capture. In this method, instead of connecting with database, CDC tools will read the logs from database and pass the transaction happened in database. So advantage of this method is there is no impact on production DB or production applications. Also, we can capture schema changes and all DML operations. So we have leveraged change capture method for data acquisition. So what is the right storage system to maintain your data lake? To understand that, let's see the problems with traditional data lake store. As part of schema enforcement and evaluation, when there is a schema change in upstream application, there is no straightforward way to change the target schema in traditional data lakes. And this will break the flow with schema evaluation. As part of the versioning, in case of any failure, there is no way to roll back to previous version in traditional data lake systems. And as part of data corruption, right? Assume you are writing the data in overwrite mode, Spark will first truncate the data in destination and then only it will try to write the data. So in that case, while writing the data, if there is any failure, truncate data is already lost. As data lake does not support any atomic transactions, we can't enclose the transactions between begin and commit like RDBMS. And traditional data lake systems are not ACID compliant. If we consider isolation, for example, when two users are simultaneously performing write operation on same table, it will not throw any error. As there is no clear isolation between multiple writes, this also leads to a data corruption. So to overcome all these traditional data lake problems, we have Delta Lake to rescue. Delta Lake by storage files, it's not a different from Data Lake. Delta Lake also stores the data in Parquet file format, but it needs an additional metadata layer to add all the transaction capability like atomicity, data versioning, and rollback to the previous versions in case of failure. So Delta uses an optimistic concurrency control method to isolate different user actions performed on the same data at the same time. So this provides transaction level isolation between different writes. Whenever there is an update or overwrite, This metadata layer tracks which files are in add state and which files are in remove state. So this is how it becomes ACID compliant. For schema enforcement and evaluation, we have merge schema and override schema options in Delta Lake. And for time travel, metadata layer will store what is the latest state of each and every transaction and also older version of the transaction. So by mentioning specific version and timestamp, we can go back to the older version of the transaction. And data quality is one of the key aspects that we are seeing it in the business currently. And Delta Lake provides the flexibility to create check constraints on column level. So these are some of the design decisions made for data acquisition and storage. Now, how to deploy data processing engine between data acquisition and storage system? As part of infrastructure provisioning, we want to talk on how we are deploying data processing engine to be available in any platform. So we want to make this product cloud agnostic, as we have many customers running their analytics workloads in various cloud platforms like AWS, Azure, and on-premises as well. So we have leveraged Terraform to provision the infrastructure in various platforms. So as Terraform works based on infra as a code, we also perform policy checks on infrastructure. Infrastructure provisioning code to meet all organization compliances while provisioning the infrastructure. So some of the example policy checks are: no VM should open ports publicly and restrict to use only specific instance types for VM provisioning. Auto scaling of cluster should not scale more than 10 nodes. So we will create policy checks config by having all these checks in place and to act on the Terraform template. So how we are deploying this product? Based on the selected environment, we will choose the respective Terraform template to deploy Kubernetes cluster with necessary ports, services, and volumes. We have launched the replica sets as part of the pods deployment to avoid single point of failure. And we have leveraged various services for Kubernetes internal communication between pods. And also, we attached persistent volumes to pods to retain the state of the application even after the restart of particular pod. It's an evident that microservices architecture clearly raised the demand for containerization. So having containerization in place, we are making sure that our product can be launched in any platforms with minimal effort. So with that, I will hand it over to Karthik to cover the solution deep dive.
Thanks, Sandeep. Hi, everyone. Now let's deep dive into solution architecture. This is the overall architecture. We use open source CDC tool, DEBEZIUM, to capture the change data from source system. As of today, DEBEZIUM will support these 5 databases, which is listed here. Kafka Connect acts as a data producer for Kafka broker nodes. Kafka Connect uses DEBEZIUM connector to pass the logs from source system and write it into Kafka broker nodes. Once it reads the data from source system, it first pushes the schema to the schema registry and then gets a unique ID for each schema and pushes this ID into Kafka along with actual data. This way, payload information in Kafka will be drastically get reduced. As business grows, obviously there will be a need to add new feature, which in turn change the table schema. Schema registry is used to store the schema with respect to the received data. By doing this, we can switch between different versions of schema. Also, this will help to prevent the breakage of downstream applications when there is a schema evolution. Spark structured streaming, which runs in Kubernetes, will act as a Kafka consumer and process the change data and schema changes into Delta Lake. This infrastructure and application platform will be bringing up using Terraform. This complete changes streaming queue and processing layer infra is running in Kubernetes. When there is a load increase, Spark can scale up multiple containers to do processing efficiently. Finally, the data can be stored in Delta Lake, which can be written on any distributed file system like HDFS, Blob, or S3. It is also possible to write it into local file system for demo purpose, not for real project scenarios. In this demo, we are using open source CDC tool DEBEZIUM, which can support only any of these 5 databases. In case if there is a need to read change data from different source system which is not supported by DEBEZIUM, then only change we have to replace DEBEZIUM with some paid CDC tool. Other than that, no change is required in this entire architecture, and this complete architecture can be reused. This is how Kafka connector properties looks like to connect with Microsoft SQL Server using DEBEZIUM connector. Number of tasks needs to be given as 1 always to preserve the order of change messages. If we increase the number of tasks to achieve parallelism, it may lead to process the deletes first and then it will process the inserts for the same primary key, which throws errors while processing the data in Kafka consumer. In our scenario, it is Spark structured streaming. Other properties are connection properties that needed to connect with SQL Server and Kafka broker nodes. Last important properties are key value converter and registry URL. Avro converter is given for key and value converter. Using Avro format to persist the data in Kafka broker helps to reduce the data volume size drastically. Each schema will be registered to the schema registry for which URL is specified in the connector properties. These are all the connector properties. One point to note here is for each table, one topic will be created in Kafka to track all the DMLs, but only one common topic will be created to track all the DDLs for all the tables under one database. This is how sample message from DEBEZIUM looks like. There will be a lot of information in actual data sent to Kafka, but for this demo purpose, I just took payload information for insert, update, and delete. In right side, here we insert one record into sample employee table in source system SQL Server. When DEBEZIUM interprets this message, it sends before and after image of the data, which in this case of insert, only after image data will be available. But for updates, it captures both before and after image. During deletes, we will see only before image. Once deleted, there is no details available in the system, that is SQL Server. So after image for deletes will be null always. The reason to understand this is our complete code logic flow depends on this information. Now let's see the high level flow of in code logic flow in Spark streaming while processing the microbatch. In data preprocessing, split the data into two parts. One will have inserts and updates and other part will have only deletes. Reason for this is schema of the payload is different in all the scenarios. But for insert and updates, we only need after image as we are maintaining SCD type 1. We don't need the before image in updates, but in case of deletes, we need the before image to know what data got deleted. Using this primary key, we must delete the data in target system. If we take after image in delete, the data will be null. So it is not possible to know which information needs to be deleted in Delta Lake. This is the reason data split is required before processing the actual data. During initial load, create a delta table and load it by excluding the deletes. As it is a new table, there is nothing to delete, so deletes are excluded during initial load. Once initial load is completed, from next microbatch, we will be receiving incremental data. Next step is data preprocessing. Once again, for incremental data and process the DDL and DML changes. DML changes will be handled using one single command, that is SQL merge. Merge command is used to handle inserts, updates, and deletes in single command based on the operation column provided by DEBEZIUM. Operation column provides information whether the record is insert or update or delete based on C, U, and D flags. In first micro batch, Spark consumes the initial load data from Kafka and process inserts updates in one data frame and deletes in other data frame. Once data is split, then take only the recent records for that particular micro batch by using windowing and rank functions. This is a sample code snippet for doing this in Spark and Scala. As a result, final data will look like this. As this is initial load for the table, deletes needs to be excluded while inserting into target. Finally, the target data in target delta table looks like this once loaded. Now, initial load is done. In next micro batch, we are receiving incremental data. Left side data is incremental data consumed from Kafka. This data may contain inserts, updates, and deletes. Also, for the same key, there may be multiple entries as well. In the sample data, ID 11 have 2 entries. Same data preprocess step needs to be repeated for all subsequent micro batches. Only different from initial load is instead of excluding deletes, we will use merge command. After preprocessing, data looks like this with only recent records on each primary key. Consolidated incremental staged data is in the left side. To handle schema evolution, schema auto merge property needs to be enabled. This property is only available from Delta Lake 0.6 and higher versions. Using merge command, update when primary key from incremental data matched with delta table and operation flag is update. Or else delete when primary key matched and operation flag is delete. At last, insert when primary key from incremental load is not matched and with the delta table and operation flag is delete. Table highlighted in orange is the delta table before applying merge. After applying merge, the delta table looks like this, which is highlighted in green in right side. We submit Spark application by talking directly to Kubernetes API servers on the master node, which will then schedule a pod for the Spark driver. Once Spark driver is up, it will communicate directly with Kubernetes to request Spark executors pods and start reading the data from Kafka topics. We have maintained Spark streaming checkpoint in file system according to the platform that we used. For example, in AWS, we used EFS, and for in Azure, we used Azure File Share. So we ensure metadata checkpointing will not be lost even during restart of Spark driver. Some of the key benefits to be noted while running Spark on K8 is dev team will have more control on building the containers with necessary dependencies. Easy to migrate the job to any environment like cloud providers or on-premises. When Spark jobs are idle, resources can be used by other application, which is not the case with other resource managers like Yarn, Mesos. Next, let's see about application monitoring. Centralized monitoring for both application and infrastructure has been built using Elasticsearch, Fluentd, MetricsBeat, and Kibana. Elasticsearch is document-oriented NoSQL DB stores that it stores the logs in inverted JSON index. Fluentd and MetricsBeat acts as an agent to transfer the logs into Elasticsearch. Fluentd is used to collect the logs from containers running under Kubernetes cluster, whereas MetricsBeat is used to collect the logs which is from node and pod metrics like CPU usage, RAM, and disk usage. Kibana is used to visualize the various metrics captured in Elasticsearch. This is how monitoring dashboard looks. Currently, we have 2-node Kubernetes cluster and 34 pod containers are running. It displays CPU and RAM usage across nodes and pods. This is our sample dev cluster. This can also be drilled down to check which pod is consuming how much CPU and RAM. Now let's see some of the notable points. With respect to DEBEZIUM, in order to track the change data, primary key is mandatory. Without primary key, it is not possible to track the change data. By default, Kafka Connect will create one topic per table with only one partition. Due to this, Spark job will not get parallelized. To achieve parallelism, Either configure it in Kafka Connect properties or create a bash script to create a Kafka topic with greater number of partitions based on each table. One topic will be created for each table under a database to track all the DMLs, and only one common topic per database to track all the DDLs. With respect to Spark, if typical small file problems are handled, when merge happens, there is no need to rewrite a lot of files. In return, this will improve your microbatch performance drastically. There are few ways to achieve this. Optimize in Databricks runtime will compact the data in Delta Lake, but this option is only available in Databricks runtime as of today. In Delta Lake OSS, write compaction logic with data change property as false. This is one of the salient features in Delta Lake. Writing this way will preserve the previous commits and overwrite entire table by evenly distributing the data. If this delta table is used as streaming source by any downstream applications, compacting data using data change property as false will not interpret streaming applications. Else, compaction will make a new commit which the downstream application will think it received new data to process, but actually it is not true. So use this property with care. Another option is to enable adaptive execution mode. This will automatically control the number of partitions while writing it into Delta Lake. Though checkpointing directory consolidates the Delta log files, in order to travel to specific version, Spark will not read checkpoint directory in metadata log. If we remove these tail commits using vacuum, then it is not possible to time travel to specific commits. Thanks everyone for joining us. Your feedback is important to us. Don't forget to rate and review our session. Thank you.